full speaker of this session, full talk, is Ruth Angus, who's going to tell us about calibrating gyrochronology with galactic kinematics. Please, Ruth, go ahead.
Hello. I think I'm sharing my screen. Okay.
Yes, we can see it.
So I'm going to talk about gyrochronology, which we haven't heard about yet so far in this session. But gyrochronology is this method that has incredible promise for providing ages for stars, particularly low mass stars like M dwarfs and K dwarfs. It could provide very precise ages so we measure the rotation rates of stars, and we think that the rotation rates of stars are very strongly correlated with the ages of stars. So if you can measure a rotation period, you can infer an age for a star. And this is extremely promising, especially for TESS, because TESS will discover many planets orbiting M dwarfs. We'd love to be able to measure the ages of those M dwarfs, and gyrochronology is one of the best opportunities we'll have to measure the ages of low mass stars. I should say, and so in this talk, I'm going to talk about how we're using sort of kinematic ages to come at this problem from a slightly different angle. But I will say that people have studied low mass stars using kinematics as an age proxy for a long time, and we're sort of building on an established corpus of work in this area. And so at Exostar last year, myself, Elizabeth Newton, and Jen Van Saders, we worked quite closely to come up with a sort of framework to use kinematics in a way that could teach us about how low mass stars in particular change over time, how their rotation periods evolve, so that we can use their rotation periods to measure their ages. Gyrochronology is still not very well calibrated for M dwarfs or for old stars. And so kinematics give us an opportunity to calibrate gyrochronology in those regimes, because kinematic ages are kind of applicable to stars with a range of masses. So the basic idea here is that velocity dispersion increases with age, and rotation period increases with age. This figure shows vertical velocity, VZ, which you can calculate if you have Gaia parameters for a star. It also helps if you have a radial velocity, although it's not essential. I can talk about that in more detail if you're interested at the end. And so here's vertical velocity versus rotation period for stars with periods measured from the Kepler spacecraft. These are data from Macquarie in 2014. And you can see that the velocities fan out with increasing rotation period, and that is because velocity dispersion increases with age and rotation period increases with age. So these two things are correlated as well. And the reason why velocity dispersion increases with age is because of kinematic heating in the disk, orbital heating in the galactic disk. And so we kind of figured, well, one thing that we could do is we could actually calculate kinematic ages for stars if we group them together by rotation period. So to calculate a kinematic age, you typically calculate a velocity dispersion, which means you need a population of stars. And then you take the standard deviation of the stars of the velocities of the stars in that population to get a kinematic age. You convert velocity dispersion to age via an age-velocity dispersion relation, and then voila, you have kinematic ages. And so one reason you might think about doing it this way is because stars with similar rotation periods should in general have similar ages. That's kind of the central tenet of gyrochronology. And by binning stars in rotation period, you can then almost bin stars by age, calculate the velocity dispersion, get a kinematic age that is the average age of all stars in that bin, and there you are, you have a kinematic age that you can use to calibrate gyrochronology. So that's sort of what we did, although it's actually not really true that two stars with the same rotation period will have the same age, because temperature or mass is also a pretty big factor in this as well. So here's what we actually did. We took a grid in rotation period in log space and effective temperature, and we calculated the velocity dispersions of stars over this grid And in this figure, the colors of the points here are the velocity dispersions. And then we interpreted velocity dispersion as an age proxy. We didn't actually calculate kinematic ages in this paper. We just interpreted velocity dispersions. And so I should say again, these data are from McCullen et al. 2014. Overplotted here are some gyrochronology models, which are a pretty simple polynomial fit to some open clusters from my 2019 paper. This is a simple gyrochronology model. It doesn't work very well. As you can see here, the black lines don't trace lines of constant velocity dispersion. They cross multiple velocity dispersion regimes, and that's because they're not good isochrones. They're not good gyrochrones. They're not a good gyrochronology model. And so you might ask, well, why am I comparing with this gyrochronology model if it's not very good? But the sort of answer there is that in general, most gyrochronology models, especially empirically calibrated ones, look pretty similar to this. We're now seeing with these data that they're probably a little bit too steep, especially in the K and M dwarf regime. But we did also compare with another set of gyrochronology models from Spada and Lansaframi. And those models are shown in the bottom panel here as white lines. I hope you can see them. And qualitatively speaking, their models seem to fit these field star data better. So I don't know if you can see my cursor, or I've lost my cursor. Well, anyway, the models flatten out towards lower masses. Like if you look at around 0.6 solar masses, you can see that the models get kind of flat there. And that seems to be reflected in these field star data. The masses here, by the way, are from Travis Berger's catalog. And the reason why the Spada and Lansaframi models flatten out there is because they actually account for non-uniform angular momentum transport in the interiors of stars, non-uniform over time and mass. And so the kind of main takeaway from this paper was that these kinematic ages, velocity dispersions, kind of provide further evidence for there being this core envelope decoupling process in the sort of internal, in the interiors of stars, which is creating this kinking and this sort of flattening out of the gyrochronology relations. Please ask me more about that if that wasn't a very clear explanation. Just ask me at the end and I can explain it in more detail. So that's kind of the result of this initial work we started at Exostar last year. But since then, and this is published in AJ, and since then we've kind of continued to work on this because we feel like it's a pretty promising method. And I think it was at the AAS in January, which seems like years and years ago. I presented some preliminary results from this, and Sebastian Pineda came up to me at the end and he suggested that I, instead of binning stars like this to make this grid, that I actually draw a box in period and TEF around every star individually, and then calculate a velocity dispersion for each star based on the velocities of its nearest neighbors. And so I thought that was a great idea, and so that's what we have started to do now. So this is a paper, this is a figure from a paper that's in prep by Lucy Liu, who's a first-year Columbia graduate student. And it shows rotation period again versus temperature. But this time, it looks a little bit different because this Y scale is in linear space now, not log space. And this figure is calculated by doing exactly what Sebastian suggested. So Lucy takes the bin in period and temperature around centered on every star, and she calculates the velocity dispersion for all the stars in that bin. And then she uses an age velocity dispersion relation to convert the velocity dispersion into a kinematic age. And so this figure shows in quite a lot of detail how the ages of stars, or the rotation periods of stars, I should say, change over time as a function of temperature. And it's a pretty kind of exquisite view into what the gyrochronology relations should look like. And we're calling this gyrokinematics, although it's a little bit of a misnomer because really these are just kinematic ages, but they're calculated using the assumption that stars with similar periods and temperatures have similar ages. And so that's where the gyrochronology side comes in. And these ages, they don't depend on very much. They just depend on like two central assumptions. One being what I just said, stars with similar periods and temperatures have similar ages. And the other one being that the velocity dispersions of stars increase over time. And those are two fundamental things that we know to be true, or at least we expect to be true on the whole. And then we choose an age velocity dispersion relation, and there are many calibrated age velocity dispersion relations that we could have used. And so that's the only sort of model dependence that comes in to this method. Now we actually take things a step further than this, and we don't just bin in 2D, we now bin in 3D, and Lucy has been optimizing bin size using a sample of comparison stars, which I'll explain in a second. So we actually bin in 3D now. We don't just bin in period and temperature, we also bin in absolute G magnitude. Log G would also work. Basically, this now accounts for the fact that stars of different evolutionary stages will also have different rotation periods as a function of their age. And so you can see the subgiants kind of light up here, and that wouldn't be possible if we didn't also bin an absolute G magnitude. So you've trusted me so far that these kinematic ages are accurate, but I can show you that they are. So we have compared these stars to a set of comparison stars which have ages measured through other methods. And the way that we calculate gyrokinematic ages for those stars is that we say you have an astroseismic star that has an age from astroseismology, and it also has a measured rotation period. You can place it on this diagram and calculate a velocity dispersion for all the stars nearby in this diagram. And so that in that way you can get a gyrokinematic age for anything with a rotation period. And here are the results of doing that. So this shows gyrokinematic age on the y-axis, and then measured age through some other means on the x-axis. And we have a few different sets of comparison stars. We have isochronal ages from Travis Berger's other catalogue that came out this year, his second catalogue. We have astroseismic ages from Victor's paper. We have some clusters compiled from the literature. And we have a couple of ages from white dwarfs with M-dwarf companions from Rocio Keenan. And there is some detail that I can explain further again if anyone's interested, especially related to the isochronal age comparison here. But in general, our gyrokinematic ages are consistent to within 1 sigma when compared with all the other alternative age dating methods. So we're pretty confident that these ages are accurate. And I should say we actually also have some more astroseismic ages to add that are older, that lie, again, on this one-to-one line. We just haven't added them yet because of a slight complication related to weak and magnetic braking. Again, I can talk about that later, but I don't have time right now. Okay, so we can show that gyrokinematic ages are accurate. They're also pretty precise. We think we have uncertainties of around 1 gigayear. And now we can use these kinematic ages to calibrate gyrochronology. So this shows rotation period versus TEF, again, with McQuillan sample in gray, as some calibration stars from clusters and astroseismology. And then you see the grid of square points. Those are gyrokinematic ages from Kepler. And the lines here, that's a new gyrochronology model, which is actually based on the Gaussian process. Sorry, this is my last slide, Victor. And just finally, I think this method has incredible promise for extending into the M dwarfs. And if we add in M-dwarfs from the MERS survey, from Elizabeth's work, then the trends actually look very promising. They seem to continue. And so we could actually start to extend gyrochronology into the M-dwarf regime. That's all. Thank you.
Thank you very much, Ruth. Also, virtual clap for a very nice presentation. Questions from the audience. We have two raised hands, so I'll take them just out of Zach Prater, please go ahead.
Hi, Ruth. Great talk. Good to hear from you. I'm curious with the age comparison plot with the systematic offset with the gyrokinematic ages and the isochrone ages. Could you say more about that?
Yeah. So one thing that I didn't go into detail about here is that we don't directly compare to the isochrone ages from Travis's paper. And the reason for that is that the uncertainties from isochrone ages are in general going to be large. And so it's actually very difficult to visually demonstrate what the relationship is between the two. And so what we actually did was we used extreme deconvolution, which is a method that models data sets as a combination of Gaussians, to effectively deconvolve the isochrone ages from their uncertainties, and so that you can see the underlying trend. And so that's why those isochrone ages, that's why they look, like they're in this kind of Gaussian shape. That's because they've been deconvolved to be a Gaussian. And they're really just there to kind of give a sense of what the systematic offset would be between these two methods. You can see there are actually some systematic offsets between a few of these different methods. There are various explanations for that. Perhaps the most important one will be that the stellar evolution models are slightly different. Our age-velocity dispersion relation might be a little off, but this shows that on the whole, things look actually pretty good. I would naively expect offsets to be much bigger than this. I hope that answers your question.
Absolutely, thank you.
Thank you, Ruth. And then we have a second question from Mayang Narang. Please go ahead.
Hi. So I had two questions. The first question is, how are you binning? So you show a 2D binning where you can you explain the concept of this 2D binning? So usually when you do velocity dispersion, it's a 1D binning. So I'm curious, and it's a very interesting way of doing it. So yes, this plot, yeah. Can you explain the 2D binning?
Yeah. So we'll just we'll pick a star. I can't quite figure out how to use my cursor to show you, but if you pick a star visually on this plot and then draw a sort of box around it, and you take all the stars in that box, you calculate the standard deviation of the velocities of all those stars, and then you convert that to a kinematic age with an age-velocity dispersion relation. Does that make sense?
Yes. And the second question was so you're converting the velocity dispersion to an age, so you must be using some empirical relation. So I was curious, what empirical relation are you using?
Yes, we're using the relation from Yu and Liu, 2019, which calibrated the age-velocity dispersion relation using red clump stars and Gaia properties. And their relation extends to much larger distances than ours. So we think that it should be valid for all the stars in our sample.
And also, so are you correcting for the galactic motion? So there would be a galactic differential rotation, right?
Oh,
so
for the sun's motion in the galaxy?
Yes.
Yes, we are correcting for that.
Okay, thank you so much.
But we're not correcting for differential motion, which I think maybe is what you're asking.
Yeah. Okay, thank you.
All right. Thank you, Ruth, for a very nice presentation. I think that wraps up at least the talks from our three speakers of this first session. We went from effective temperatures to Rossby numbers to galactic motion. So I think that was actually very interesting to tackle the problem of accurate characterization of stars from these very different angles.